Hi all, good afternoon from Barcelona. Welcome to a new Rhino user webinar. This is Pedro Cortés, and we continue this series of videos where we discover new workflows in which Rhino is in some way involved. This webinar will focus on the usage of Rhino and Grasshopper for the creation of Metaverse content. And this presentation will include a brief introduction to the Metaverse and research projects illustrating the creative process. To cover this amazing content, I can introduce Odysseas Georgiou, Michail Georgiou, and Ioulios Georgiou. All of them are part of SEAMLEXITY, an office focused on developing and applying computational tools assisting both design and construction processes. They lead as well a workshop at the University of Nicosia, and some of their students have been awarded in the architecture category and the top Metaverse build. So, well, with this introduction, I'll let them start presenting. And I'll be here, as always, working in the shadows, collecting the questions you might have for all of them. So, guys, you can start wherever you want.
Thank you very much, Pedro. Okay, can you see my screen?
Sure.
All right, so here we go. So, hello, my name is Michail Georgiou. I'm an architect, computational designer, an associate professor at the Department of Architecture at the University of Nicosia in Cyprus. I'm also a co-founder of SEAMLEXITY. I would like to thank, on behalf of the entire team, Michail Europe and Pedro for this invitation to talk and deliver a Rhino user webinar for the Metaverse. Before we start, I would also like to very briefly introduce the team. Today, we will be delivering this webinar along with Odysseas Georgiou, engineer and computational designer, adjunct faculty at the University of Nicosia and co-founder of SEAMLEXITY, and Ioulios Georgiou, architect, computational designer, adjunct faculty at the University of Nicosia and collaborator of SEAMLEXITY. The webinar is structured into three parts. During the first part, I'll try to set the context in which we are working and provide some information on our research and methodology. I will also be presenting a selection of student projects for the Metaverse. Ioulios will then cover a typical workflow from Rhino to the Metaverse, followed by Odysseas, who's going to be talking about the use of Grasshopper for creating and optimizing Metaverse content. Okay, here we go. So as I have already mentioned, we all teach at the University of Nicosia. It's the largest university in Cyprus, the largest in Southern Europe, teaching in English with 20 research centers and more than 100 programs. We co-teach all digital design classes for architects and interior designers at the Department of Architecture. A very interesting building, a renovated shoe factory. I hope to get you get the chance to visit us someday. You can have a look at the interior of the building and the department's recent output through our virtual exhibition. I will post the link in the chat later. We call this our pre-Metaverse work because we have actually used Rhino and Enscape to create this set of virtual environments. Back in 2019, we have launched a master program in computational design and digital fabrication in collaboration with the University of Innsbruck, which the entire team is currently teaching in. I'm also going to post some information about this one. The program has a unique physical digital structure, or physical virtual structure, if you like, in the sense that while it is distance learning, students are required to attend 2 large workshops, one in Cyprus and one in Austria, respectively, to gain hands-on experience in digital and robotic fabrication. The University of Nicosia has been a leader in cryptocurrency education and research since 2014. So it wasn't a coincidence that we have been involved with designing for the Metaverse. We are actually currently participating in the development of 2 courses related to designing for the Metaverse for a new master's program titled Metaverse Systems under the umbrella of the Open Metaverse Initiative, recently launched by the University of Nicosia. In parallel, and as Pedro has already mentioned, and apart from academia, we are also active in the local industry through SEAMLEXITY, a computational practice. SEAMLEXITY uses advanced digital tools to provide tailored support to designers, fabricators, and building contractors from concept to realization, aiming at de-skilling complex design, construction, and digital fabrication tasks. Our portfolio and engagement ranges from large-scale high-rise buildings to small-scale product design assignments, such as jewelry and sculptures. Okay, so let's get to the subject. Unfortunately, I won't go very deep here as we have a lot to cover today, but I will just stand to a few key facts about the metaverse before we can move on. We understand the metaverse as a collection of virtual worlds where users can interact. Ownership is the driving force based on Web3, open networks, and blockchain technologies. And the ideal scenario would be to become an enabling layer connecting physical and virtual worlds, able to transform and support social culture and commercial activities. Creating for the metaverse definitely involves new opportunities for architects. While some core architectural skills and processes might be applicable to the field, new skills and a shift in mindset and methods is additionally required. We need to clarify at this point that in our research and work, we see things from an architectural perspective. And while certain terms and methodologies might be common practice for other disciplines, like game developers, for example, this is not necessarily the case in our field. So to kickstart and explore the metaverse, an educational intensive one big workshop was realized at the University of Nicosia back in March 2022, offering the opportunity to undergraduate architecture students to engage with custom software workflows and metaverse platforms towards proposing and constructing interactive virtual environments. We aim to answer practical questions, such as can CAD software be implemented for the creation of metaverse content? And if so, what are the workflows and limitations involved? What is the potential role and possible applications of computational design tools for creating for the metaverse? The workshop was hosted at the Department of Architecture of the University of Nicosia in Cyprus. As part of the workshop, the students were voluntarily asked to submit their proposals to the Next Top Metaverse Build competition. And 2 proposals were actually submitted at the competition and both got awarded. The competition has been relaunched this year for those of you that might be interested. I mean, we can post some links as well later on. Okay, so we have realized through our research early on that online 3D modeling tools offered by various metaverse platforms, usually called builders, are currently limited in creating, editing, and optimizing builds. As such, as a result, we posed the question of whether CAD software, like Rhino, right, could be implemented for the creation of metaverse content. We obviously choose Rhino and Grasshopper to test this hypothesis, as these are the tools that our students and ourselves are more experienced and comfortable with. To streamline the process, we prescribed 3 pipelines associated with specific file types within which the students could research and develop their projects. Each team selected a pipeline and was requested to visit the corresponding metaverse platforms and familiarize with their technical features, requirements, and limitations. In parallel, students were asked to develop a consistent information workflow to transfer their designs from Rhino to the corresponding metaverse platforms, effectively assessing and validating the Voxel, the Polygon, and the game engine pipelines, identifying distinct paths to a large number of metaverse platforms. 5 proposals were developed along these 3 pipelines. The results include 1 proposal in the Voxel pipeline for Sandbox, 2 proposals in the Polygon pipeline for Decentraland, and 2 proposals in the game engine pipeline for Mon. I will continue by briefly describing the 3 pipelines and the corresponding proposals. For the Voxel pipeline, geometry was created in Rhino and Grasshopper and translated through Magica Voxel before imported into VoxEdit's Sandbox's native builder. Game mechanics such as animations and interactions were prepared in GameMaker, Sandbox's custom game design tool. The software enables add-ons such as buttons, waypoints, and avatar bots, some of which were incorporated in the design. Under the Voxel pipeline, we had one proposal titled Control Shift, a customizable and gamified virtual NFT gallery space that can foster interactions between visitors and engage the audience. The project was designed, adapted, optimized, and tested for Sandbox. The concept pertains to the customization of virtual space, and the project represents a shifting gallery made out of different types of block geometries. Some blocks are animated in space, some are portable, and some are fixed. For the Polygon pipeline, geometry was modeled and optimized using Rhino and Grasshopper before exported via a GLTF plugin, including materials and texture. The model was divided in parts and uploaded as a series of assets into Decentraland's native builder. Interactive elements such as buttons and NFTs were added via the builder. The use of PBR materials enabled seamless transition of materials and textures. And this is actually the pipeline we're going to be demonstrating later on. The Polygon pipeline was used for developing Lush Proposal, an awareness platform designed to inform, donate, and buy NFTs that benefit environmental development and the preservation of endangered flora, a garden space, which is used for gathering, education, and play. The project was designed, adapted, optimized, and tested for Decentraland. The main design element of the proposal are the trees that represent various species. 3D models of these trees can be acquired by the public and populated, planted elsewhere in Decentraland, therefore contributing to the initial cost, educating the community and preventing further flora extinction. The trees were modeled in low polygon resolution and were generated in Grasshopper using an L system algorithm. MetaMaze is the second project developed for Decentraland under the Polygon pipeline, a gamified virtual space that aims to engage visitors through a maze type of environment. It implements interactive features of real-world escape rooms, such as keys, riddles, buttons, etc., into a metaverse environment. Finally, the game engine pipeline. For the game engine pipeline, geometry was modeled and optimized using Rhino and Grasshopper, including materials and textures, and was exported to Unity. A Unity template provided by Mona was implemented to translate the model file into the virtual environment. Colliders, interactivity elements, materiality, animations, and lighting features were added via Unity. I have to say that a lot of these things that I'm describing here, we're also going to revisit them later on the hands-on tutorials by Ioulios and Odysseas. Vortex was developed using the game engine pipeline for the Mona Metaverse platform, and is a generic exhibition space for built environment presentations. A fractal space that enables the visitor to teleport inside the exhibits to experience one-to-one scale buildings on display. And Odyssey is the second proposal developed for Mona using the game engine pipeline, an allegorical proposal that aims to engage the visitor in a journey of experiences and surprises. Odyssey aims to cause extreme spatial stimulation to its users by embracing the potentials of animation and lack of physics in the metaverse environments. Now, regarding this, the technical framework of the workshop, because we did deal with other things as well, all teams have managed to realize consistent workflows and translate their projects from Rhino to interactive metaverse scenes. Additionally, a number of peripheral areas of focus were identified and explored, such as optimization, computation, consistent use of materials and textures, and interactivity. The workshop outcome verifies the appropriateness of Rhino and Grasshopper for creating metaverse content. In addition, the result supports the classification of the 3 workflow pipelines we proposed. Finally, demonstrating competences in the peripheral areas of focus can help mitigate the limitations currently imposed by the majority of metaverse platforms. So in the following parts of this webinar, we aim to emphasize exactly on these design enablers, as we call them, because we do believe that they do make a difference when it comes to maintaining the design intent. Okay, before I conclude this first part, I would like to thank the guest lecturers, the guest tutors, and of course all the students that participated in the workshop, and you've seen their work. And I would also like to inform you that the results of the research presented or the workshop have been published in a paper titled Metascapes Architectural Quests in the Metaverse. Of course, I'm going to post the link later on. Now, moving to the hands-on parts of the workshop, I would like to give you a brief introduction of the example project Ioulios and Odysseas will be using in their demonstrations. The project is called Bloom, and it was the output of a competition in Cyprus within the framework and activities of the European Capital of Culture 2007. After the submission of numerous international proposals, 8 of them were awarded and selected for realization, and Bloom was one of them. You can see it here in pictures. And since Bloom does not exist anymore, we thought that it might be a good idea to provide a virtual version of it for the Metaverse. So during the hands-on demonstrations, we will illustrate one of the 3 pipelines, Polygon, to show the steps needed to prepare Bloom for the Metaverse. We are going to use Decentraland as a destination platform, and both Ioulios and Odysseas presentations will guide you through various steps involved in the process. As such, you're going to see the applications of materials and textures, scaling, colliders, optimization techniques, exporting and viewing, and finally the use of Decentraland's native builders. And I won't be talking anymore, as I'm sure that you can't wait for the hands-on part. So I will now pass the presentation to Ioulios. Thank you for your attention.
Thank you, Michail, for the introduction. Hello, my name is Ioulios. I will be showing a brief example of how to export the 3D model from Rhino to Decentraland while using some optimization techniques, the PBR materials, showing the GTL format, what it is, and also how to optimize the model and change different settings in Decentraland. So Decentraland, we have to say a few words about it, is one of the most established Metaverse platforms in the last 2 years. We are using the Polygon pipeline, so you can see that the graphics have this low polygon resolution, which makes it available to most computers in general. So Decentraland is basically a huge virtual real estate, which is made out of land parcels. So one square pixel you see on this map is basically one land parcel, which is 16 by 16 meters. A larger group of parcels is called an estate, and a larger one, a district. So the land parcels can basically be bought, sold, and rented on the Decentraland's own marketplace, or they can be also be bought in external marketplaces like the OpenSea, which is the general marketplace for NFTs. So as in most Metaverse platforms, Decentraland is based on the Ethereum blockchain. It has its own native token, which is the mana. And the land parcel in the estate is also considered native Decentraland tokens. So coming into Decentraland, we have, you can easily just start exploring on your own to see how it is. It's quite user-friendly. And Decentraland has its own marketplace. What is about that? In this marketplace, you can not only buy or sell land, you can also sell any kind of 3D model, which is basically shown as an asset. An asset is the keyword for Decentraland. So an asset could be a wearable, it could be an accessory for your avatar, and it can also be a 3D model of a building. And all these can be part of the marketplace of this NFT environment. And any kind of 3D model that basically is made for Decentraland has to go to Decentraland's own builder. So Decentraland has its own native builder, which you have to use to import your own models, custom models, which will be assets. And in the builder, you can also add native interactive elements of Decentraland to make it basically part of the Decentraland game. So in the builder, we have to say that in order to build for Decentraland, you have to own or rent land, but you can still use the builder to test and create stuff and export them for the marketplace. So the builder basically lets you create a scene first. So you have your own scenes as a user, and you can make them. So in order to use it, you have to log in. You can either have a Meta wallet like MetaMask, or you can also use Fortmatic to simply log in with your email address. So in order to do so, you can start by creating a scene. For example, this. And it asks you for a number of parcels. So as I said before, each parcel is 16 by 16 meters. You can make a scene of max 32 parcels. But I will go away now from Decentraland and go to Rhino to see our Bloom model that Michail mentioned and see how much parcels we actually need first. So this is an open poly surface that was made to create as part of the modeling process of the Bloom project. So the Bloom project is basically almost 9 by 9 meters. So one parcel of 16 by 16 meters would be enough to host it in Decentraland. So I put a simple rectangular plane of 16 by 16 meters just to keep in mind how far we can go. And you can notice I positioned it at 0.000, which is basically also the midpoint of a scene of the Decentraland builder. So it identifies the world coordinates you will export from. An important thing to notice is that Decentraland and basically most Metaverse platforms have limitations because of their capabilities. And Decentraland has very exact limitations on the models. So basically, this is from the Decentraland website. You can see that according to the number of parcels you are using, you have a limitation in height, in number of triangles. So triangle meaning a triangular mesh, number of entities, of bodies, and also important, the number of material and number of textures used. So in our case, for the Bloom, we need one parcel of land. So we have a limitation of triangles of 10,000. So if we start with this model now, we have to basically first measure the triangles that it will create. So by using the polygon count component in Rhino, it's doing a forced triangulation on the surface, and we can see that it's about 25,000 triangles, which is way exceeding the limit. So this is basically why we need different types of optimization. So one of the ways to reduce the number of triangles is the quad remesh, which is basically also a new component in Rhino 7. So this will make any type of object into a quad mesh. And it also asks you for a specific number of target to reach, number of quads. So in our case, I would go really low for even 1,000, because this was a singular surface. And I also want to add some thickness and make an offset of the surface, because until now we weren't able to make a double-sided visible surface for Decentraland in this method that I will be showing, but Odysseas will address this later. So anyhow, we made now a quite low, I have to probably repeat the process. Yeah, I didn't press it before. It's doing the quad remesh now. So now I have my first surface, and now I have it go through the new mesh. So the new mesh, if we count it now, It's about 1,692 triangles, which is basically much, much better, and we can still do a lot with our scene. So as I said before, I still want to offset my mesh and make it a solid. And I have now a mesh with a thickness, which should be something now, if I use the polygon count, a little bit more than double. So yes, I have now 3,784 triangles, which we are good to go. So now I would like to export this in Decentraland, and we have to talk a bit about material first. Basically, there's a couple of ways to do material. We can just simply make standard colors as a lot of components in Decentraland and make a new material, a simple plaster, and putting a simple color on it. And you have to be careful that this material has to be appointed to the object itself and not to a layer. So the material has to be adjusted to the object. So now that I have the material, I have to export this into a GLTF format. And this is key for, in general, Decentraland and most Metaverse platforms. The GLTF format is basically derivative for graphics language transmission format. And it's a standard file format for 3D scenes and models. And it can either be exported as a GLTF, which is a JSON file, or a GLB file, which is binary. For this export, I will use a plugin called GLTF Bin Exporter made by Ask Dorsch, which you can find at Food for Rhino. We should post the link to it as well. And how that will work is that we export this component, export selected, as a GLTF. And now we can upload that in Decentraland. Basically, we can also use the GLTF viewer to test our models before uploading them, because sometimes materiality can go really wrong. So it seems that the material is fine. And we can use now Decentraland to post it. So I now need, again, back to the builder, one scene. So I'm making a scene of one parcel into Decentraland. And this is how the builder looks like. I have a series of assets that these are native to Decentraland, and this can be anything from a simple tile, which you click and it's placed inside the builder, or you can also use other more interactive components like an Instagram social media icon, which will act as a link to something more. So in general, you have a lot of native objects that you can also edit in this builder. For us now to import the model, we have to make our own asset pack this way. So we create our own asset pack. We have to upload from our current computer. So we have the GLTF. It's uploaded. You can already see a preview, see the number of triangles that we had before, the number of materials, and to continue, create an asset pack. So we're basically making a new pack with specifically that component inside. So by clicking it, it will place it directly in the point that it was exported from from Rhino. So this will be our model. And this we can also test as a user in Decentraland, how it would feel like. So I can walk around it, and you can notice now that I can also walk through it, which is not what we want. This is due to the fact that this object isn't identified as a collider. So the collider term is something that for a game designer must be a given, but for us architects, it was really something new. So collider is basically is an attribute to a 3D model, which makes it act as a boundary which you wouldn't be able to walk through. So we can go back to Rhino and change that. So in order to make a collider, it's quite simple. You actually have to make a copy of your current model. So I'll copy it and place it in place. And I have basically two meshes over each other, which are identical. And I have to make it a collider by changing its name. So Decentraland is basically identifying the ending of an object's name as a collider. So for example, if I call this Bloom, I have to finish it with _collider. In this way, Decentraland will recognize this geometry as a collider, and it will be also shown as invisible in the builder. So that's why the collider has to be over the other component. So this, of course, I can hide for now. And I can also use this chance to make a PBR material. So about PBR materials, we have to also have a look. So PBR materials are basically physically based rendering, which is also new in Rhino 7, which means that the material describes the visual properties of a surface in a physically plausible way, such as realistic results are possible under specific lighting conditions. So you have a lot more options to describe a material, like its transparency, specularity, emissions, bump, and more. But more specifically, if you want to make transparent materials or emissive materials, you need to, for Decentraland, you need to go for a PBR material. And PBR materials can be found also online, and usually they are made of multiple texture files which describe all these different aspects of a PBR material. So in Rhino, we can make a PBR material. We can either create a physically based material from texture files or just make it from scratch, which we're going to do now. So there's a lot of settings of all these aspects that we talked about before. And we can assign textures for, let's say, the base color. We can choose a metal texture. And we can also add more components, such as, example, the metallic effect from another texture. And you see that it's now basically making it more shiny under correct lighting conditions. So we can export now again. Sorry for that, I have something extra there. So I have basically my mesh and my collider in one. Now it seems orange because of the collider, but it will be invisible once we export it for Decentraland. So I'll select both of them. And I will export my selected file. Again, as a GLTF. And I go back to my builder. And I can add more to my asset pack. So it has, of course, more triangles because it has a collider inside, 2 texture files that we use, and 2 materials. So I'm saving the asset pack. And now I can place this here. So basically, I have to remake this again because we made a simple mistake. Basically, an important part of the material is alpha transparency, and we have to tick this off in order to make solid components. So I have to export this again. And I already have this here. So this is what I wanted, the metal component and collider, and we have to test the collider now. Again, can I walk through it? Now I'm being blocked by the collider, so the collider has worked. So to conclude, if you wish to add transparency to the material, it won't be achieved using the capacity. Even though it seems that way in the preview, you actually have to use the alpha transparency component of the PBR, which is here. You have to tick this, and you have to go all the way down to capacity and change the alpha to something much lower in order for this to work. So having said that, I can now give room for Odysseas to show you a more advanced way to export material and multiple material from Grasshopper. Odysseas, you may take it away.
Thank you, Ioulios. So hello from me. I am Odysseas. I'm taking over from Ioulios left to present an alternative method of exporting geometry for the Metaverse from the Grasshopper plugin. Moving directly from Grasshopper to GLTF format offers an additional design control, obviously, better optimization methods, and a direct visual response. Optimizing mesh, as mentioned before, is quite crucial to maintain models within the limits of the Metaverse platforms. We'll be using the Shape Diver plugin for this webinar. Shape Diver is a plugin for Grasshopper that lets you upload and display your Grasshopper models online, but it also allows you to export files of various types directly from Grasshopper. So I'll be using the same BREP that Ioulios used before, and I will use two different meshing methods, and I will explain the difference in the course. So the first one is the basic mesh BREP component from Grasshopper. I'm going to attach the custom settings here. I'm setting all of the parameters to 0 so that I am only left with the maximum edge parameter to control. Here's how my mesh looks. So it's important to stress out that the GLTF export works with triangles and not quads. So I need to compose this into triangles. This is the mesh triangulation component that triangulates the quads. Then I'm going to connect this onto the deconstruct mesh component in order to count my faces or polygons. Here on this panel, you can see the face count, which should be reflected on the models that I'm going to upload in Decentraland later. So now we have a direct visual output of the quality and smoothness of our mesh and the face count, which is quite easy and fast to know how heavy is our model before we export it. So I'm just going to leave it somewhere here. And I will now add some material onto my mesh. I'll be using the Shape Diver GLTF 2.0 material, which handles PBR materials, as explained before from Ioulios. The PBR allows us to export physical aspects like glossiness, emissions, and transparency. But this one also allows us to export double-sided materials, which is something that we couldn't achieve with the previous Rhino exporter. These allow us to have actually the half the polygons on offsetted mesh, which makes our designs much more optimized. So I will connect a basic color swatch onto the basic color factor. And I'm going to attach this material onto the Shape Diver GLTF2 display. This component here is used to display the Grasshopper or Rhino models into their online interface, but it's also used to export to GLTF 2.0 formats. And then I'm going to connect my triangulated mesh here. Turn some things off. So you can see that the material is reflected onto the Rhino viewport. I can also add a glossiness, a metallic factor, and you can see how this changes onto the viewport. Now I will proceed with adding some textures on this. First, remove the color. So I will be using a basic brick texture from Rhino's render content. This has to be pasted as a path, and it has to go into the import bitmap component from Shape Diver. This needs to go onto the base color texture, and you can see how this is reflected onto the Rhino viewport. You can also see that it's a bit scaled up, and I'm going to explain how this can be controlled. We're using a scale non-uniform component from Rhino, which is empty basically, with a couple of sliders. This gives a transformation data, which needs to be fed onto the transform texture UV component that comes again with Shape Diver, and this takes our mesh, and the mesh goes onto the GFTF display, and now I can control my textures size. The same way you can control various transformations as rotations, flip, mirroring, and these kinds of things. So now I have scaled my texture. I can proceed with exporting. So if you right click here and click on Save GLTF, this is it. Now you might notice that this becomes a binary format now. So it does not export the text GLTF, it exports binary, which is the same thing, but more lightweight in a binary format, so it cannot be read easily using a text editor. And now I'm going to import this onto my viewer. This is how it looks. So, and if I check the report here, it says that I have 4,418 triangles, which should correspond to my metrics here exactly. So now I'm going to show a second meshing engine. I'm going to disconnect this and connect it here. This is the try remesh component. This was initially embedded in the Kangaroo plugin, but now it's part of the Grasshopper. It generates meshes from triangular meshes from scratch. It makes much more sense to use this kind of edging to generate triangles, since GLTF takes triangles. There's a drawback, however, that the textures from both Grasshopper and Rhino are not recognized, because the Grasshopper cannot, but the shape diver plugin cannot understand the UV coordinates of this triangulation. But if I turn it on and I also plug it here, you can see that I get an equally smooth mesh as before, but with a quarter of the triangles that I had before. So the total mesh count is much less than with this component. So I'll make this a bit more advanced. I have this cluster that we generated here that basically culls faces from the mesh in order to remove some triangles and create openings, or have faces that we can add transparency on. So I'm going to attach my triangular mesh here. And you can see that this has removed some triangles. I have a slider here to control. And I also have the offset mesh component to give a thickness to my mesh. And I have another cluster here that creates the tree that was presented before. It was part of the workshop that we did. So we generated a very lightweight tree. Because we were limited by the polygon count, and we wanted to attach lots of trees. We have this, which is quite lightweight. This cluster here outputs the leaves or the branches and the trunk. The trunk is going to have one material, so I can join it to one mesh, but I'm going to leave this as multiple faces, as I'm going to give a different color to each one. So I'm then extracting the center of each mesh, and I'm sorting it according to its height. So I'm getting its Z value, and I'm passing it through the Grasshopper's gradient component in order to get a different color for each branch or leaf according to its Z value. And I'm also numbering here the Z value in order to get a name, a specific name for each material. And I'm passing it through this material component from Shapediver to generate the 78 materials for each of these objects. I'm creating a simple color material for the trunk, and I'm creating a different material for the shell, and I'm adding some glossiness here. And now for my openings, I need to create some transparency. This is achieved using the alpha mode, which is now set to opaque. I need to add the blend option, which basically blends the color swatch and inherits the transparency from here. So you need to change this transparency, this alpha here, in order to get transparency on the material. So now if I add this here, maybe add some metallic factor, I have a transparent material. Next, I have to combine all the mesh geometries using the weave component into one output. And I'm going to do the same with my material. So geometry goes here, and material goes here. Now, for some reason, the GLTF display component does not work with tree structures. So if I graph this, you see that I get a warning which says that it does not support tree data. That's why we need to have exactly the same list length in geometry and material. So if you're using geometry that has the same list that has one single material, then you need to repeat your list and make it equal length. More strangely, you need to graph this to get it to work. And I need to sometimes reconnect it. And you see how this looks in the Rhino viewport. I have now control over the different parameters of my tree here. Turn it off. I can change the height and make it more dense, or I can control the number of openings here, or maybe the transparency. And then I can right click here, save as GLTF or GLB. And I'm going to give it a try on my viewer. So this works all fine. I've done another remix here in Decentraland. So this is a version with the pipes and a gradient, a much more complicated model. Oops. So you see how this looks. Just adding a gradient on each of the pipes the same way as we did with the tree. So this concludes the tutorial, and I believe we're open for questions. Thank you very much for listening.
Amazing work, guys. Congratulations. Yeah, I have some questions for you. Young Colby, are Rhino layers used in Decentraland?
I can answer that. So not in Decentraland, but even if you work in Rhino with layers, the idea is you have to, each object has to have its own material attached to it. So even if you work in layers in Rhino, which we all probably do, you still, and you have a lot of components, if you want to export all of them, you will still probably have to export them first as an OBJ, so that directly each material is attached to the object. And then you should export the OBJ into the GLTF format if you work with layers in Rhino. I hope that answers the question.
Yeah, well, at the end, all the objects needs to have their own texture or material.
Yeah, their own material.
Yeah, okay.
So you wouldn't have, yeah.
Yeah,
no,
CD Gomez asked, sorry, CD Gomez want to ask as well is, can Ioulios talk about how to determine the number of triangles? That is, how to know how many triangles you can get in a model?
Yeah, so I've shown this in the beginning. If that's the question, can I share screen real quick again?
Sure. Yeah, of course.
So basically, you have a limit. This is provided by Decentraland itself. So according to the parcels you use, so in my example, we use one parcel, 16 by 16 meters. So it depends on the size of your model first. So you determine based on the size of your model how many parcels you need. And depending on that number, you have the maximum number of triangles you can use. And to determine that from your model, you select basically any model you have, and you do the polygon count command. And that's a forced triangulation, basically, which will tell you if you export this in Decentraland, it's 7,500 triangles. I don't know if that answers the question, but yeah, that's what I understood.
I'm sure it did. Yeah. Omar Atef asks you, do Decentraland accept different types like breadths, mesh, vectors, or just meshes?
I can take this. It only accepts mesh. So GLTF is a simple either binary or text format that translates the mesh into coordinates and materials and textures.
Mm-hmm.
So Decentraland and most of the other pipelines that we talked about, either to take OBJs or GLTF, it's mainly mesh.
Okay. And Raymond asks if it's possible to export an animation from Grasshopper into Decentraland. For example, if a parametric slider falls, that shape outwards and inwards. Any of you guys? Do you know if it's possible to export an animation? Yeah.
No, the animations have to take place either by scripting, programming, or within the Decentraland builder itself. So we were able to export meshes from Grasshopper and geometry.
So even if you use a game engine?
An Unreal Engine.
For Unreal or Unity, you cannot export. You cannot export animations from that game engines.
No, we haven't. Not for Decentraland, as far as we are aware. We've done it with other platforms that support Unity directly.
Okay.
But not from Rhino. So the animations are done in Unity, for example.
Yeah. Okay. So Isaiah asks, what are some more pros and cons for ELTF pipeline versus game engine pipeline?
Okay, I can take that one. First of all, they lead in different platforms, right? So we have associated pipelines with platforms. So if you go with GLTF, you can end up in Decentraland, for example. If you go with game engine platform, you can end up in Mona, the ones we've shown. In general, we realized that game engine based metaverse platforms tend to have better graphics, if I may say so, more realistic graphics, not better. I mean, it's not. So if you are aiming for a more realistic, let's say, result, maybe and more capabilities when it comes to interactivity, then maybe a gaming engine platform is the way to go. On the other hand, it really depends what the outcome is or what you want to achieve. Maybe Decentraland is one of the most known platforms, right? So if you want to go to Decentraland, maybe you have to go through the pipe. No, you have to go through the Polygon pipeline. So I think it might need to work backwards, what you want to achieve, and then you choose one of the pipelines that we have identified. And maybe there are other ones that right? We didn't manage to discover.
I think that your answer applies also to this question. Does this workflow also work with other Metaverse platform servers?
Yes, in my presentation in the beginning, we did show the platforms. So we obviously tried other platforms as well, right? So Sandbox, and then we tried the Spatial, and if I'm not mistaken, yeah, Crypto Voxels we tried. So we tried at least 6 to 7 different Metaverse platforms through our pipeline.
Yeah. Well, thinking about the future, Quatsimod wants to know if you can be hired as an architect or designer to design a metaverse. So, can you be in the near future, meta architect? What do you think?
Ioulios, you can answer this one.
Yeah, I'm not hired as a meta architect, but sure, I can answer it. There are already some architects that have taken it, are focusing solely on the Metaverse platforms in general. I think the most famous example is Big, for example, were commissioned to design the Vice headquarters in Central, which is a high-profile example of that. But there are some young architects who are starting to focus to be meta architects.
And yes, we could be hired as Metaverse architects if there is a project. We would
of course, yeah. I mean, we already have one, to be honest, in the works, but we didn't show it as a future project.
Okay.
For example, maybe I can elaborate on that, because we have a project that should be realized in the future, but needs funding, and the client decided to give us that project as a Metaverse first, so which is in the works before it actually happens in reality. So that may be an interesting way to work on Metaverse as an architect.
So this project is actually a real project in the Metaverse. In which one, if I can ask?
Well, it's going to be for the Mona Metaverse.
Okay.
Due to the graphics, that's basically a choice of the client. We're prepared for various platforms, including Decentraland, but it made sense for him to go for Mona. It has the animation, the gaming graphics, the high render, so that's what they chose.
So which pipeline has the most cross-platform or compatibility potential at the moment?
Compatibility with Rhino.
Compatibility, I guess that Isaiah refers to other platforms, I guess. In terms of this workload.
The one we demonstrated is for the Decentraland platform. Right? I'm not quite sure if I'm answering the question. If he could clarify a bit more, maybe we can answer more specifically.
Okay. In the meantime, well, have you thought about creating a plugin to automate all this process of like checking these geometry limitations?
No, not really, but
no?
Yeah, we can plan it.
Okay, any other question from the chat? Okay, so I think we can let it here. Yeah.
Sorry, but I saw a good question which I wanted to actually show, and maybe I could answer. It's from Dino.
From Dino?
One of our own. Yeah. So can I read it, or do you want to?
No, you can read it.
It's basically just asking if the the collider model has to be identical to its twin, the real model, in terms of faces and mesh. And it's true, it doesn't have to be identical. You can the smart way to work would be to really reduce the mesh of the collider to its absolute minimum, because you won't be seeing it, and you would in this way reduce the triangles you're using. So Yeah, that was a good question. That was it, I think.
Okay, so you have to take into account the number of triangles of this collision geometry as well.
Yes, the collider, you have to, because you're uploading it, even though it's invisible for the Decentraland, you have to take into account that it's made out of triangles as well.
Well, that's important.
Yeah. Yeah, actually, based on this, Pedro, one of the things we really try to do, and one of the obstacles you have when you're designing for the metaverse, is all these limitations that are imposed by the platforms. So what we try to show in this webinar is actually how you can overcome those limitations and be able to deliver what you want to deliver. Because most of the times you need to reduce so much your models to upload them, then they end up being something else than what you wanted to design in the beginning. So the whole idea of optimization and computation is to help the designers really be as close as possible to their models during the design phase to what they're going to end up being on the metaverse.
For sure.
And the allowance you have is based on the size of the land you have. So the smaller it is, the less triangles and less materials you're allowed to use. So that's why it becomes very important, because land is expensive in the metaverse.
Okay. Okay, guys. So thank you very much for your time, for your effort.
Thank you for inviting us, Pedro.
Thank you, Pedro, for inviting us. Yeah.
Okay. Well, to the attendants, see you in next webinars. Thank you, guys. Again.
Bye-bye.
Thank you, everyone.
Bye.
Hi, everyone.
Bye.
Thank you.